Imagine a tennis ball magically appearing on the other side of a solid wall. Today we will learn what quantum tunneling is, why it happens, and where we use it. We will first compare classical and quantum ideas, define the probability wave, and then examine the tunneling mechanism. In classical physics, a ball rolling up a hill must stop and roll back if it lacks enough energy to reach the top. If the barrier is too tall, the ball is always contained on one side. Quantum mechanics tells us that tiny particles, like electrons, behave differently because they are also waves. We use the idea of a wave function, pronounced psi, to describe where we might find a particle. The square of the wave function tells us the exact probability of finding the particle at any specific spot. If the wave function psi is 0 in a region, the chance of finding the particle there is 0. Now, let us imagine a tall potential energy barrier, which is like a wall the particle cannot classically pass. Even if the particle's energy is less than the height of the wall, the wave function does not immediately drop to 0 inside the barrier. Instead, the wave function decays rapidly as it passes through the solid barrier. If the wall is very thin, a small part of the wave function still exists on the far side of the barrier. This small, non-zero wave function value means there is a chance the particle instantly tunnels through the wall without ever having enough energy to cross over it. This transfer based on probability, not force, is called quantum tunneling. We can see this in a worked example where a particle approaches a very thin barrier. You will notice the wave's amplitude is strong entering the barrier but much weaker when it exits. The difference in amplitude represents the low but real probability of the tunneling event happening. This process is essential for nuclear fusion, where hydrogen protons tunnel through huge electrical barriers inside the sun. The technology also enables devices like the scanning tunneling microscope, which we call STM. The STM uses tunneling to create images of individual atoms on surfaces. To summarize, quantum tunneling occurs because particles behave as waves, giving them a small probability of penetrating energy barriers. This effect is purely quantum mechanical and proves that particles do not always behave like tiny, solid objects. Tunneling is vital for modern technology and for sustaining the life of our stars. Keep exploring the strange and wonderful rules that govern the quantum world. Generate your own educational videos for free at eduvids.vercel.app.